SMT3 examples. Like I just want to talk a little bit about site-in transformation, which was mentioned briefly in class. So let me just do that very quickly. Okay, so basically, what an SMT solver, or let's just say even a SAT solver is. Let's just talk about SAT solvers, and then later on we'll talk about SMT. So SAT solvers basically do this. They'll take a Boolean formula. So it's something that takes a Boolean formula, and then it'll give you whether this Boolean formula is satisfiable or not, right? So what do we mean with this? A Boolean formula, you can think about that as a Boolean function from all of the variables involved in the formula to 0 or 1, right? True or false. So it is some function involving a number of variables that gives you true or false. And SAT means that some assignment of these variables is true. So we have some values of these variables for which this function gives us true, right? So is there some input for which we get true? So the SAT solver is going to give you or tell you whether there is some input or not for which the answer is going to be true. And if there is not, then it will give you unsat, and it will give you a proof of that. So we talked about that, like as I talked about that in class. We mentioned site-in transformation. So there is this constraint that SAT solvers take in a formula in a very specific format. So the formula has to be in a format which is called 3CNF, which means that the formula needs to be in this particular format. So you'll have A or B or C and then another clause with this form and so on. So basically this 3CNF format says that the formula will be and of a number of clauses, right? And each one of those clauses is going to be some variable 1 or variable 2 or variable 3. And you can optionally have one of these variables negated. So it can be basically be variable 1 or a not of variable 1 or a not of variable 2 or a not of variable 3. So basically you can have formulas of this kind, A or B or C, and not A or D or not C maybe, or something like that, right? So you're going to have and of a number of clauses, and each clause is going to be odd of a number of terms, and each term is either going to be a variable or not of a variable. So in fact, write like that, so that it's a bit more standard. So we don't have term, 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 and the term is just going to be either var or you're going to have not of var, right? So var is our variables. So SAT solvers require a formula in this particular 3CNF form. Now, so here's the question, right? So if you're saying that SAT solver is going to take a formula in this particular form, is there some catch there, right? So like, can we always convert a given formula, any given formula, into this 3CNF form, and can we do it efficiently or not, right? Because we saw that, with this specific, we saw this other specific form in class called BDDs, right? With BDDs, it turns out that the SAT is constant, right? But of course, converting the formula into BDDs is going to be, like, we found that it was actually itself at least NP hard. I mean, otherwise, how do you get SAT to be constant time, right? Then you solve P versus NP. So is there some such catch with this 3CNF form, right? So firstly, I want to show that even, like, I want to say that even with a formula being given in 3CNF form, we don't know of any polynomial time algorithm. In fact, all the definitions of SAT assume that the formula is in 3CNF form. When the definition of SAT basically shows you that it is NP, it actually assumes that the formula is in 3CNF form. So we know that even if the input is in 3CNF form, this thing is actually NP hard, right? But it still remains the question, like, can we actually convert any arbitrary formula into this 3CNF form efficiently or not, right? So turns out we can, and that is called the site-in transformation. So there is several spellings of this. I hope that this one is one of them. So it will take you any arbitrary formula or any arbitrary Boolean formula, and it's going to give you a 3CNF representation, or another formula in 3CNF which should be equisatisfiable. So what does this equisatisfiable mean? It basically means, so we say the two formula F and G are equisatisfiable. I'm going to write it like this, although I think there is some other, something like this as well, right? So we're going to say that F and G are equisat if F being sat is equivalent to G being sat. So to show that two formulas are equisatisfiable, you have to show that if F is satisfiable, then G must be satisfiable, and if G is satisfiable, then F must be satisfiable, right? So what we're trying to find then is an equisatisfiable 3CNF formula for any given arbitrary formula. So because if you can find that, then we know that, okay, we can always convert any formula into 3CNF form and then go from there. So that is the Stiefel transformation. So how do we do this, right? So let's think about what a formula is. So formula is going to be some expression involving or. So this means or, this is and let's say not, right? So let's just say that the formula is in an expression involving these three. And you can, of course, you can take other things like implies, you can take equivalent and so on. And I'm going to not deal with those, like it goes through for these cases as well. In fact, I probably won't show too many cases here because I don't know if I have enough time for that, but if you want me to, I can. So yeah, so basically a formula then is going to be some expression involving these, right? So let's take an example. Let's say that we have P or actually let's start with and, right? So let's say that P and Q. Okay, let's actually include implies here, right? And let's say that we're going to say that this implies P or R, let's say, right? So let's just work with this as our example formula, right? Or okay, actually, just to include, make this not R. Yeah. So yeah, so this is our formula, right? Now, one can think of this as being a tree with subtrees being subformulas and so on, right? So if you're familiar with things like CFGs and things like that, and like parse grammars and so on, so you can sort of have a parse tree for this. The reason that I'm going to draw this out, it's not necessarily like needed. You can intuitively think of them as subformulas, but that will help us to show the fact that this cycling transformation is efficient more easily, like more intuitively, I think. So we can draw that. So we can say that this is the top level of that, or the top level is going to have this implied operator, and then you're going to have or, and then you have P, Q, and so on. And then similarly over here we have, sorry, this is and then we have or over here. Then we have P, we have not, and we have R, right? So this is basically our formula in this sort of a tree-like form. Now, what we do is we take all the non-trivial subformulas of a given formula and create a new variable for it, right? So, for example, over here we have the non-trivial subformulas as being this P or Q. So we're going to create a new variable. Let's call this, let's say X1. So this sits on this node. This refers to the non-trivial subformula P and Q. Similarly, we have a non-trivial subformula not R. So let's call this as X2. We have P or not R. So that is X3. And then this X1 implies X3. So that is our final whole formula X4. So, okay. So when I say non-trivial, I mean non-single variable. You can sort of, I mean, yeah, this entire formula is going to still be taken as one variable, right? So we have this sort of like one variable for each node in this graph in some sense, right? So we have our original variables and we have added extra variables for each one of these nodes, right? So now we can capture the semantics that says that, okay, this X1 is going to be satisfied or it's going to be true if and only if this node evaluates to true. We can capture a semantics that says that by some Boolean formulas, right? So if you think about it, if you have some assignments of P, Q, and R, you can sort of go bottom up along this graph and evaluate what the final value of this Boolean function is going to be, right? So as you go bottom up, you're going to get values at each one of these nodes. So R is going to be something, and then not R is going to be something. You have some value of P when you're going to get a value of P and not, sorry, P or not R over here, and so on, right? So we can capture this concept that the value of this node, this value of x1, is going to be 1 if and only if P and Q is 1, right? So the value of this, each one of these subformulas is going to be true if and only if the related like relations between its children hold, right? So we can say something like this, for example, x1 is true if and only if P or Q, right? x2, in fact, this is equisat, right? So x2 is equisat to not R, x3 is equisat to P or, and now notice that we have this children here. So instead of having this entire formula here, we're going to just say x2, right? So P or x2, and x4 is going to be equisat to so x1 implies x3, right? So we have these things. So now we have basically got a tree, and we have one node, like one variable for each node, and we have a bunch of expressions. So if I replace these with, say, the equivalent operator in terms of a Boolean operator, then we have a bunch of expressions which captures the fact that the value of each one of these variables is going to correspond to some value when you evaluate this expression bottom up, right? We evaluate this 3 bottom up. So does this make sense? So I'm going to assume that's yes. I mean, if you have any questions, just stop me, right?
So like you are describing a transformation, right? Like, could you
like lay it out as steps or something?
What?
Or, are you asking me to lay it out as steps? Or?
Yeah, could you just give me kind of a step? Yeah.
Yeah. So intuitively, what we're doing is 2 things here. So add vars for, so assume that your tree is your input, right? So that is fine, because I mean you can pass this to a parser or whatever. But yeah, so add vars to each node, let's say, to each node, which is basically a sub formula. And then you can basically, each node is an operator, right? So for each node which is an operator, so node is an operator, which is op, we're going to have 2 children, and those 2 children will have some variables, right? So either those variables are going to be your original variables, PQR and so on, or some of these xi's that we added. Right?
Like variables will always be leaf, right?
Yeah, so I'm saying we are adding variables to each one of the nodes as well, right? So it's either going to be one of those added variables or the leaf variables.
Oh, okay.
Right. So once you have done this first step, then you know, when you take each node, just the local part of your tree is going to be look like some operator, and then you have some node here and some node here, and these nodes will be labeled by some variables, right? So either you're going to have so we can say that like these leaf nodes are labeled by their corresponding variables, let's say. So it's going to be labeled by some variable over here. So it's going to be labeled by some v1 and v2, right? And we're going to transform this. So we're going to take this and say that, okay, this guy is, say, labeled by v3. So you're going to say that, okay, v3 is equivalent to v1 op v2, right? Does this make sense?
Yeah.
Does this make it a little bit more concrete for you? Yeah.
Yeah, this is like that abstract syntax tree or something like that.
Yeah. I mean, yeah, it's basically it's kind of like it's instantiation of an AST in some sense.
Yeah, okay.
But yeah, basically once you do this, then you have so you're basically including all of the variable values for the subformula. So you're saying that, okay, we have one huge formula, and instead of just talking about the lowest level variables, let's add new variables for each of the subformulas. And let's just track the, like, the relation between these variables and all of your extra variables, like, so these subformula variables are of your original variables, right?
Right.
That is what we're doing over here. So now notice that now if I AND all of these, if I consider all of these as some formulas, and if I AND them, right? So if I AND them, let me just create more space. So this step is basically convert each local part into formula as above, right? So that's step number 2. Now, yeah, so if once we have these formulas, if we AND them, and if I add finally this x4, because remember this x4 is what represents our entire formula, right? So if we do this, then what we get is going to be equisat to x4. So this is my claim. The claim is that if you have our original formula f, which was this entire thing. So let me just copy that over here. So let's just say copy. Let me just make it smaller. Yeah. Right. So yeah. So right. So basically we had this formula and this was our f. And what we're claiming is that f is going to be equisat to this, right? So is this claim clear? And can you imagine what the proof is going to be, or do I go through that in some sense? So okay, so basically,
it's clear. Basically, like you are just setting those variables to be. Yeah, you're just creating extra variables and then ANDing them.
yeah.
Yeah.
So the I mean, it being equisatisfiable is in some sense clear. So for example, over here, this PQR, if we have, so like if I give you a satisfying instance of this, so like if I give you values of PQ and R for which f is evaluates to true, then for that particular value, x1 and x2, x3 and x4 are all going to evaluate to some particular values, and finally x4 is going to be true by definition, right? And we can just read this value set x1 to that value, read this value set x2 to that value, read this value set x3 to that value, read this value set x4 to that value. So we can go down just setting the values of these extra variables and finally get the true value for this x4, and that is going to give us a satisfying assignment for this whole formula, like the PQR and extra variables that we've added. Similarly, if we have a satisfying assignment of this formula, then we have some values of PQR, and we know by construction that since x4 itself is going to be true, we know by construction that f of PQR has to be true, right? So yeah, you can.
I have a question. Like, how does this grow? Like, is it just
yeah?
So, and my guess would be
second claim. Yeah. This claim 2 is that we have linearly many formulas, or claim 2 is that this grows linearly.
So it's not n log n, it's n.
Yeah.
Okay.
Right. So notice that each one of these formulas are bounded by a constant size. So each one of these formulas are at most, so you're going to have one operator here, one variable here. So that is at most 3. I mean, in the case of not R, that will be true, but that is at most 3. And then you have x1 equivalent to these things, right? So each one of these is going to be at most 5. And also notice that you have linearly many number of these things, right? So you have precisely one for each extra variable that you've added. And each one of these extra variables correspond to one node in your tree, right? So you have at most as many of these things as number of nodes you have in your tree, right? So this is clearly linear. So is this clear?
Could you repeat your claim?
Yeah. So let me just write it. So let's just call these added formulas. So each added formula has some bounded size, has at most 5 size, right? Because it looks like this, right? So it looks like some V1 equivalent to V2 op V3, right? So we have 1, 2, 3, 4, 5, right?
Yeah.
Yeah. And the second thing is that like the number of formulas is going to be so we have one formula for each variable. So one formula for each xi, right? And we have one xi for each non-leaf node, right? So number of formulas is basically size of your input tree, is right?
Right.
Yeah. Now, this will basically tell you that this if you call this, let's say the let's just call this entire thing f prime. So size of f prime is going to be O size of f, right? It's going to be linear. Is this clear?
Doesn't the size of input tree grow like it will have some height, right? And
Yeah, but if you look at it, like we have exactly okay. So I mean, there's two ways to do it. So one is just I can say that this is, since our tree is our input itself, then the size of the input is just the size of input tree. But if you define your input, let's say as the string representation of your formula, right?
right.
So even then, notice that each node in your tree corresponds to one character,
Huh.
ignoring things like parentheses, right?
Okay, okay. So you are, yeah. So it's
Hmm.
not in the size of variables, you are saying in the size of the
Yeah, in
total.
the size of the formula. Yeah.
Oh,
So
okay, okay.
even when we talk about things like, say, the complexity of SAT or 3-SAT, we always talk about the size of the formula, right? So in 3-SAT, the size of the input is considered as the number of clauses you have, because each clause is only going to be some 3 terms wide, right?
Right, right. Okay,
Yeah,
makes sense.
yeah. Okay. So now you have this. So now basically this f prime, this notice that this f prime basically looks like some formula and some formula and some formula, right? So we have this form. So if we can convert each one of these to CNF, if we can convert each one of these to 3 CNF, then we are done, right? So I'm going to claim that we can do that. I'm going to show you a few cases. Actually, I think I can show 4 cases. Let me show you this one. This particular case, right? So let's say that you have this x4 is equivalent to x3 implies x2, right? So the first thing that we do is we are going to convert this to, we're going to split the implication both ways. So we're going to say x4 implies x3 implies x2, and we're going to say that, okay, x4 is implied by x3 implied by x2, right? So we're going to say and of that. So we go from this to and of these two formulae. So let's look at each one of these. So x4 implies x3 implies x2. So let me just not, so that we don't get confused with the brackets. Although we don't need to. Okay, in the second case we do. So This one, what we can say is we can basically use the definition of implication to break this. So we can say that, okay, this will basically be equisatisfiable with, yeah, so these are equisatisfiable. This will be equisatisfiable with not x4, or you're going to have, and over here you're going to have not x3 or x2, right? So not x4, so implies, you break it by saying that, okay, A implies B. So this is just an aside thing. This is too light. Yeah, so A implies B is sort of like, we can even say that it's defined as this, right? So not A or B, right? Either A is false, then your entire thing is true, or if A is not false, then B has to be true. Like, so there's two cases in which your implication is true, either when A is false or when B is true, right? So we're just using that to separate this. And notice here that these braces are redundant, these inner brackets, and then we have some 3CNF term, right? So this is a 3CNF term, right? So if we consider this to be 1 and 2, 1 is done. Sorry. Okay. Yeah, so 1 is done. Similarly, let's do the same thing for 2. For 2, what we'll get is basically, we'll have to flip everything around. So we have x2 implies, sorry, x2 implies x3, and this entire thing then implies x4, right? So this will be, if we do the same thing, it will basically be not of, and then we do the same thing over here. So not x2 or x3, and this not of in this entire thing, and we'll have, or we'll have x4, right? So now the problem is that you have this not over here, right? So this is not in a 3CNF form. So you'll have to basically use De Morgan's. So if you use De Morgan's, then what you get is x2 and not x3 or x4, right? And then you can use distribution. So you'll get two terms, x2 or x4, and you'll get not x3 or x4. So you again get two 3CNF terms. So in 3CNF, a term like a clause can have less than three things, because you can always just say that the fourth thing is like an extra added variable, which is always defined to be false or something like that, right? So yeah, so you get 3CNF terms here. So notice that in the second case, we're also able to reduce it, but we got two terms, right? So from this one formula, we actually got three terms here. So this was the implication case. Now you can do the same sort of thing for each one of these, each one of your operators that you have that you've chosen to like care about in some sense. So you can do it for and, or, not, all of those things. And for each one of them, you're going to get some, you're going to get some general formula for like A is equivalent to B of C, right? So in general, so this is going to be our step 3 in some sense. Convert each formula A equivalent to B of C to 3CNF form. So then notice that we are done, right? We are done because our original formula was a conjunction of these formulae, each added formula, let's say. So we had converted F to, okay, so let me just make it better. So convert each sub formula in this F tilde, right, to this form. This gives us our final site in representation F tilde. Yeah. So then we are done, because this f prime was going to be some c1 and c2 and c3, and we have converted these to c1 tilde, which is in 3CNF, and c2 tilde again in 3CNF, and so on, right? So we have got finally a conjunction of 3CNF formulas, which is by definition like just a 3CNF formula, right? So yeah, so we have this is the Seyting transformation. Is this clear?
Can you scroll a bit up?
Yeah.
I just want to see one thing. Yep. Yeah, now it's okay.
Yeah. So notice that like since so you're going to have in general, so let me just one thing I want you to notice, like this final step 3 is always going to be some constant time step, right? Because I mean you can just have a table, right? Because you're going to have some finite number of operators, and each formula is going to just be A is equivalent to B of C, right? So it doesn't matter how complicated this step is, it's always going to just involve 3 variables and 2 operators, and so you can always just consider this as a constant time step. So you can it doesn't matter much if you have to introduce 10 terms to represent this in 3CNF, although you won't, like you can do it in 3 or 4 terms for most of these things. But yeah, so this complexity of this final step doesn't come into the picture, is basically what I'm saying. So yeah, are there any questions about 3CNF?
No, not for me at least.
Sure. Okay. All right. So now let's come to SAT solvers and SMT solvers more specifically. Right. So now we're going to talk about this thing called SAT solvers and SMT solvers, right? So SAT solvers, like I said, is something. The SAT problem is defined as given a Boolean formula. So a Boolean formula. So let's say this is a formula from B to the N to B, where we are saying B is going to be 0 or 1, right? And we are saying that we are asking it, does there exist some x1 dot 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 xn, so that f x1 dot 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 xn equal to 1. So this is what we are asking. This is a SAT problem, right? So now what SMT is basically is a generalization of this problem. It's called satisfiability modulo theories. Right? So what does this mean? This, like, we know what satisfiability means, right? But what does modulo theories mean? So what you have here basically is going to be some theory which is going to define some object which is more complicated than 0 or 1. So if you look at the SAT case, then we have implicitly defined what this 0, 1 thing is, right? So we have defined what true and false means, and false means, by defining semantics of these operators, right? So they're defined by the semantics of and, or, not, and so on, right? So what we have is basically some variables in a space where the space can take like you can have various values from this space, and we have defined the semantics of some operators on this space, right? So what we have essentially is something like some set, and we have some relations on this set. And by this, we have defined in some sense what Booleans are, right? So if you want to sort of generalize this SAT solver to things which are other than Booleans, like say, for example, integers and so on, then we need to like create this common language of what we mean by, how do we say what we mean by integers? How do we say what we mean by real numbers and so on, right? And that is basically what we mean when we say theory. So theories is going to be just this thing. It's going to be a set, and you're going to have some relations on this. and you're going to define what these relations mean by some axioms, right? So for example, for Boolean logic, you can have axioms like distributive law. You can have things like De Morgan's law and so such things, right? So involution in such axioms. So for integers, for example, you can have your, so for integers, you can have things like your set will be natural numbers in axioms, maybe it's like Peano arithmetic or something, right? So for example, two examples. So S is equal to B, relations are and or not, right? So when I say this is relations, I can also say that this is going to be some functions, right? Functions from S to the K to N. So I can also define it that way. These two things are equivalent. I mean, you can say that. So S to the K to S functions. And these axioms is going to involve these functions. So your functions is going to be your operators. And then you're going to have some axioms. In this case, might be things like involution, distribution, etc. Then for another example is S is going to be N, and you're going to have your operator is going to be some, say, successor plus minus, whatever you choose to take. You can you can look up logic and or okay, I think logic books will have it in definitely will have it. I don't know if like what kind of number theory books you need to look at, because I don't know that. But yeah, if you look at any logic book, you'll get like some very clear definition of S in these sort of terms. S as like a set, some operators on that set, and then some axioms defining how those operators behave. Right. So things like Peano arithmetic. So yeah, so what SMT solvers are basically, SMT solver has a bunch of built-in theories. Usually these are things like integers, so theory of integers, theory of, say, it doesn't have a separate things for natural numbers, but it's got like integers, rationals, etc. And it's going to solve the same problem. So you're going to have a formula. So the SMT problem is basically going to be, you're given a formula, and this time this formula is going to come, like it's going to have inputs from all possible things which your SMT theories support, right? So if you have an SMT solver that supports the integers and rationals, it can be something like Z to the N cross, say, Q to the M. And then the output of this formula is going to be 0 or 1, right? So, and your question is the same. Are there some, are there some inputs x1, xn plus m such that f x1, xn plus m is going to be equal to 1 or not, right? Yeah, so this is basically your SMT thing, and then SMT solver can solve these queries as well. How? Well, that is, there are some really interesting algorithms for that, but like yeah, okay, I'm taking up way too much time, sorry. And yeah, so one of the few things that you should know theoretically about SMT solvers before we go on and show them is that these solvers are allowed to return SAT. So it says that, yeah, it's satisfiable. Unsat, where it says that it can prove that this formula is unsatisfiable. So SAT means that it is found as assignment. And unsat means it's found a proof. And it can also tell you something like inconclusive. Right? So this means that, okay, it can't determine, it can't tell either way. Sorry, what am I writing? Right? So this is the allowed sort of returns for the SAT solver. And the reason we have to allow a search solver to return incons is that some kinds of queries in your SMT formulae can actually be like it might actually be undecidable to check certain kinds of SMT formulas, right? So note that over here, when we say this function is like this, we're also actually allowed so this is what is known as the first order thing. We are also allowed to quantify over these things. So I should have mentioned this before, but in F, you can also write things like you can also have things like for all and there exists, where when you're saying for all and then some things such that something else happen, these some things need to be some variable belonging to some set for some theorem. So you can quantify over variables. So you cannot quantify over things like lists or sets or something like that. Would be second order. So this is first order logic. Yeah. So and then your SAT solver can tell you SAT and SAT on inconclusive. So basically, an example would be, you are, so in some sense, your formula F is going to have variables which are going to be int, q, such things, or booleans, such things, and you're allowed operations on them, plus, minus, star, etc. So you're allowed some boolean operation, like all sorts of operations, greater than, less than, equal to, and so on. And then you're also allowed quantifiers, existential, for all, and so on. So you have operators, quantifiers. And when you pass this entire thing, your SAT solver is going to either give you SAT, unsat, or incons. Right? So is what a SAT solver does, is it clear?
So just to confirm, like we can use these SAT solvers to, or rather, can these SAT solvers also prove statements? For example, like a typical theorem in number theory.
Yeah. So that's where this idea of things being first order comes in. So if your statement can be expressed as a formula of this form, then yes, right?
Yeah.
So for example, if your statement says something like for all primes, such, right? So then you can reduce that to something like for all numbers, if it is a prime, such and such things happen, right? Yeah. Then you can express this as a formula like this, and then you can pass it to a SAT solver. Whether the SAT solver can solve it or not, that really depends on what's going on inside and what algo they're using. It might turn out that doesn't fall into the decidable fragment of first order logic, and the SAT solver can't actually tell you the answer, right? So there is no guarantee, but you can definitely make that an input to a SAT solver and then pass and see what happens. The SAT solver might not give you an answer, or even if it can, it might just take like a few million years. So that is
one guy did this, like he tried proving some unsolved problems using SAT solvers, I guess. I'd read an article long time back.
Yeah, so I think like there is an entire
occasionally successful, like some theorems he was able to prove.
Yeah. So there is this entire thing called interactive theorem proving, where people so sir mentioned this triangle where there was this other leg, other side, right? So sir had this triangle of scalability and such things. So there was one leg which was interactive proofs, right? If you remember.
Yeah.
So they actually do use things like SAT solvers to do things like I don't know how much it has been integrated, but it is being people are definitely trying things like using SAT solvers here to take care of small lemmas or small case bashing and such things, right? So definitely you can't ever expect a SAT solver to be able to prove all theorems for you. because
Yeah,
of course,
not all, obviously. Huh.
yeah, because that is like undecidable, right? The decision problem is first of the decision problem
It's
is
brute force, right?
Mhm.
You can still brute force it, right?
Yeah, but you won't have any termination guarantee, no?
Oh, okay.
So this is a result, I think, effort decidability.
Yeah, actually, could you explain me this thing? Because I
Which
always
thing?
thought that if you have a SAT thing,
Hmm.
you have a SAT statement, you can just try all possibilities, right?
So
And
yeah, you can do that for this thing. You can do that for say something like Boolean satisfiability, right?
yeah, for Boolean, yeah.
Yeah,
Talking about Boolean.
yeah. So there you can always brute force, but if you have a
Uh,
number theory statement, how like you can't brute force over all numbers, right?
yeah, I mean, but you could transform that into a SAT thing, right?
No, you can't always. How can you like? I mean, yeah, sure. If your thing is over, say, 32-bit integers,
Ha ha ha.
but
Yeah.
that is not integers, right?
Mm-hmm.
Yeah,
True.
yeah. In fact, CBMC, that's why it uses a SAT solver. It doesn't use an SMT solver. It converts everything to like internal bit representations and works with those.
Okay,
And in
okay.
fact, modern SAT solvers are really efficient at working with formulas that come from bit representations. They have a lot of heuristics which are designed for those things.
Mm-hmm.
Um, yeah,
Oh.
in fact, I think the best floating point solvers that we have actually do that even. But yeah, basically, if you once you go into like real mathematical objects, then things are much more difficult.
I don't know. Like, won't it still? Okay, yeah. Real numbers are not okay. Yeah, makes sense.
Even natural numbers is undecidable. You can try like
Yeah,
encoding.
actually, I got confused because there was this thing that you could convert any kind of problem into a SAT problem, any NP complete problem into a SAT problem. So, but then I
Yeah, that's what
realized
I'm
that
saying. Yes.
real numbers can't even be represented in a Turing machine. So,
Yeah, so
yeah.
so that is even there, and even if you think about like just FO formula over natural numbers, some
Hmm.
of them can be like they're not SAT, like they're sorry, they're not NP hard. That problem is even undecidable, right? Like
Hmm. But
so.
yeah, for some problems, it still might make sense to, for example, you might, like if you happen to encode Goldbach's conjecture in 32-bit integers, it might still be of value, I guess.
Yeah, and there might be some problems which you can actually solve in finite number of times, and you can formally maybe even define an island of tractability in which you can operate, right?
Mm-hmm. True.
And that's why we do SMT solvers. Like there are that's the entire idea. Like okay, I mean in general we can't do this, but in real life, in most cases, can we still do something?
Hmm.
That's the entire motivation behind like making something that is supposed to solve an undecidable problem essentially.
Yeah, actually, I had one more question, like, but I don't know if it's related, but is there any SAT solver which could output like it's probably SAT or probably unsat instead of giving me a hard guarantee, but more of a
I
probabilistic?
mean, you'll have to very formally define what you mean by that, but let's talk about that a little later on.
Okay.
I just before that, I want to ask you guys like, how long are you free? You'll have to give me an answer. I'm not going to propose something and then.
I am free till 6:30, but I would like if we could wrap it up by 6:50.
Yeah. So let's do that then. So that is why I wanted, like, I stopped you, Harsh. I'm sorry because I have to
Yeah,
go through
no
some other
problem.
things.
I
Yeah.
understand. Like I myself have to do stuff, but we can discuss this later, I guess.
Yeah. So let me just save this and yeah, we can discuss this later. Okay. Okay, so are there any other, okay, we closed it, but are there any other questions regarding what a SAT solver is and the theory and citing transform, anything like that? Or I can go on to like some code and stuff. So
yeah, I think you can move on to
yeah,
coding and stuff.
Yeah. So yeah, let's show this thing. So basically, this is some program called Z3. So I don't know if you can see this. yeah, so it gives you some of these things. And so what this Z3 does is basically it will take in like a SAT query. So that is basically some SAT formula. And then it will give you SAT or unsat. And you can also like ask it to print out the model and so on. There are various other like output options that we're not going to go into, things like printing out the proofs and such things. But in general, what you can use it to is that you can use it to solve some systems of very complicated equations, or you can say check whether they're satisfiable or not, right? So this is the idea. So one of the things that, okay, actually I had to open this again. One of the things that I should have talked about before I close this is what is the input format to most SMT solvers. So of course, like there doesn't need to be a standard, but thankfully there is. This standard of like all SMT solvers follow this standard input format, which is called SMTlib2. So if you have a program that uses or prints out SMTlib2 formulas, then you can just like switch out solvers. So SMTlib2 is basically a syntax for specifying SAT queries, so SAT formulas. The syntax is kind of like Lisp, where instead of saying f of a comma b as you would in other programming languages, you say f a b, right? So function, everything is closed inside a bracket. The first thing represents what function that you're going to use, and then the next space separated items in your bracket is going to be each one of the arguments to the function. So if I want to say something like, and this goes for things like operators as well. So if I want to say something like a plus b times c, I'll have to say it like this: plus a, and then another bracket, and then star b c, right? So some prefix Lisp-like notation over here. Okay. So it might be very confusing if you have not like used this previously, because you have to do some mental work to keep like going back and forth between whatever you're used to in this format. But hopefully it'll get clear slowly. So, okay, so let's look at some. So, I mean, I'll give a link to the full syntax, but I mean, I won't go over that over here. But instead, let's look at some examples so that we can make this somewhat quicker, right? So, one of the things is that in SMTlib2, the way it's defined, there is no declaration of variables. The only thing you can declare is functions. So, any declaration is a declaration of a function, right? And the variable is going to be a one array function, zero array function, right? So if you think about it, what is a variable? So a variable is something that just has a constant value, right? So there is something that does not take any input and gives you an output value. So in that very weird sense, or you might, yeah, it is kind of a convoluted and roundabout sense, but in that sense, it's a zero array function. It does make sense because it fits into a very general framework, which I won't go into, but what we define variable as is a zero array function. So we are declaring some variables over here, but the command is going to be declare fun for declare function. And then the syntax is this: you have the name of your function, which is the variable. And then this is going to be a list of, so you can see this, by the way, right? Is the Zoom okay?
Yeah.
Just one question, by the way. Is Z3 strongly typed or weakly typed?
Z3 is strongly typed. So more precisely, SMTlib2 is strongly typed.
I see. Thanks.
Yeah. So, sorry. Yeah. So almost all SMT solvers use this thing, and this is like strongly typed. Yeah. So, so in fact, the thing is that they don't even call it types; they call it sorts, which is it's like a member of your particular this from this theory.
Yeah, I got it.
Yeah.
From model theoretic.
Yeah, right. So yeah, so basically coming to declare functions, the idea is the syntax is function name, and then you have the input like signature of your function. So if this was an actual function, you could have said some things like int. That means that your function is going to take in 2 integers, And then finally you have the the output type of your function. So this is going to be just one integer in our case, right? So we want to define a zero array function, which means that our inputs are going to be nothing. We don't have any inputs, and our output is going to be one integer. So this entire convoluted thing, all it's saying is that x is an integer variable. Similarly, we have y is an integer variable, right? So now let's, okay, by the way, semicolon is a comment, and I think list also uses semicolon, I'm not sure. But yeah, it's semicolon basically means comment. Yeah, so now we have come to this assert thing. So this assert command, what it does is it'll tell you your SAT solver to add whatever formula that follows into its table of assertions, right? So so you're going to, like, the way the SAT solver works is that internally it's going to maintain this table of assertions. So it's going to have so like this like F1, F2, and so on. And whenever you add an assertion, this is also added in. And whenever you call the check SAT to check whether the formula is being checked, like whether everything is satisfiable or not, what it checks is this F1, F2, F3, the AND of all of these, right? So in some sense, when you add an assert, that is basically added as an extra conjunct to whatever is existingly inside your SAT solver, right? So you can do assert this, and it will basically add this particular extra constraint or formula to your SAT solver. So what does this say? This says two things are equal. What are equal? X and y plus 1, right? So plus y1 basically means y plus 1. So what we are saying over here is x equals y plus 1. Right? And then the other comment, let's ignore that. And then what we do is we pass two commands, check SAT and get model, and then we exit, right? So check SAT will actually run the SAT solver to check whether this thing is satisfiable or not. And then get model is going to print out the satisfying model if there is one. Otherwise, it's going to throw an error. So let's run this. And the way you run it is very simple. You just do Z3 and then, okay, let me just clear. So you just do Z3 and then the name of the file, simple ins, right? And it says SAT. So this is coming from the check SAT thing, and it says SAT. And this is going to be this thing, like, so you're going to have a model for this, and this model basically tells you what you should define your X and Y to be, so that it is going to give you a satisfactory thing. And this is basically y should be 0 and x should be 1. That makes sense, right? So x is equal to y plus 1, so y is 0, x is 1. So it's giving us a model. So now let's add another assertion. Let's add that, okay, x should be less than y, right? Now we know that this cannot ever be true, right? There are no two ints such that one int is like one greater than the other int, and yet one int, that same int is less than this first int, right? So like it's clear that these two should give me unsat, right? Let's try that. Yeah, it gives us answer and then gives us an error because we're still trying to like get a model from this, right? So is this clear to all of you so far? I guess that's yes.
Yeah, it's a yes.
Okay, so let's go to some more complicated examples. So let's, I mean, I have, how much time do I have? I think my
8 minutes.
8 minutes, right? Let's see if I can do this in 8 minutes. Otherwise, we'll just have to talk to Sir and continue this next week, maybe. Yeah, but basically, I'm going to take a mod2 counter. A mod2 counter is going to be this system. I'm going to try and define its transition relations in like SMTlib2, and then see if we can check some things about it. I don't know if we will do, but basically we are going to have 3 things for the state. So let's say x0 and x1. And yeah, let's not worry about the reset right now. So we're going to have 2 things in a state, x0 and x1. And the initial state, so this is a declare func. So sorry, we're going to use a define func here. Yeah, so what this is going to do is it's going to define this function. So difference between declare func and define func is that declare func just declares something, and define func will actually allow you to add in an expression for that particular function, right? So basically says that init is a function with inputs x0 boolean type, x1 boolean type, output bool type, and the value of this function is given in integers, right? So of course, this
how
is
do
not
we
like this.
define cases when defining functions?
Yeah, so you'll have to do things like, so if you want to say, so in fact, we'll see this in the very next one. So if you want
So
to
does
say
it have to
something,
be stuff like if x
yeah.
belongs
So
to
there is no if. You're going to have to do things like some P1
implementation.
implies P2,
yeah.
not P1 implies something else, and so on, right?
I see.
Yeah, and similarly, we are going to have this thing over here. So again, let me get rid of the resets. I'll post an example with the resets in there, but I can't. I want to simplify this thing so that I don't make too many mistakes right now when live coding under time constraints, essentially. Right. So over here we are defining the initial thing. So this is the function that's going to take in two values of x0 and x1 and is going to be true if that represents an initial state. And what I'm saying is that, okay, the value of this function is true if x1 is 0 and x2 is 0. And sorry, x0 is 0 and x1 is 0. That means the initial state in our case is 0, 0. Right? Now we're going to similarly define a transition relation. It's going to take two values of x0, x1, two pairs of x0, x1, and it's going to give us true if they represent a valid transition. So in our case, a valid transition is going to basically look like 0, 0 to 0, 1 to 1, 0 to 1, 1, right? So let's just, and then back. So let's just case dash that. So if we have 0, 0 and 0, 1, then, okay. So I don't need to do this actually. I can just say not of this. Yeah. So if you have, say, both of them are 0, right? Then what we want is that so both of the input variables, so x00, x10, the input x0 and x1, they are 0. So then what we want is the output variable should be 0, 1, right? So we want x0 to be 1, so x0, 1, and not x11, right? So similarly, if we have x, so if we have 0, 1, so that is this, then we want 1, 0, so that would mean not here and this, right? Similarly, if we have 1, 0, so that is this case, then we'll want to have 1, 1, so that would be this case. And if we have 1, 1, then we want to have 0, 0. Right? Yeah. Okay. And what we want to do is we want to do AND of all of these things. Right. And let's not miss a bracket here. So now we have declared something, and now let's just yeah. So I wanted to show you something that actually relates back to some of the BMC stuff we were doing last week, but I don't think I have too much time. So I'm just going to show you one transition, what it looks like. Yeah, so let's just declare some variables. We'll just copy this thing here. Sorry. Yeah, so let's just say that we have x00, x01, (1, 0, 1, 1), right? So basically, okay, so x00, x01 is the x0 in 0 and 1 state, x111, x10, x11 are basically x1 in the 0 and 1 state, right? And we're going to encode that by saying these asserts. So we're going to say init x00 and x10, and we're also going to assert that trans of x00, x10 x01, x11, right? And then let's do a check sat get model. Okay. Yeah. Okay, it's tran, not trans. And I made a spelling mistake in it. What? Okay. This. Okay, I think I'm not listening. Oh, sorry. Yeah, finally. I'm sorry about that. Okay. Yeah, so as you can see, it says sat and it gives you a particular case in which this can happen. So we are saying that, okay, the initial state, we're going to say that x0 and x10 represent the initial state. And then we're saying that these two variables are talking about the state that you get after one transition from the state. So it says that, okay, x00 and x10 are both false, right? So that means the initial state is 0. And then what we're saying is that x01 is true and x11 is false, right? So that means the next state after that is 1. So that is correct. And now if we add another assert that says that, say, assert that like let's say that after 0 we are directly getting 2. So we are getting let's say that x11 is true and x10 is false. This should not happen. And yeah, it says answer. Right. So was this clear? I'm sorry, I think I'm way over time. Hello?
I'll have to go over it again.
Yeah, sure.
But yeah, the idea is clear.
Yeah, so the mistakes that I made mainly was some small syntax things. So things like this is just a single parenthesis is not allowed, because then it thinks of x00 as a function that has no arguments. I mean, it thinks of x00 as a function application, which trips it up basically. But yeah, I mean, and these should have been bools instead of ints and so on. So yeah, is it is the idea? I think that must be clear. So are there any other questions? Hello? Okay. If they're not, I'll stop sharing. I think I've taken too much time. So are there any questions? Give me a no then.
No questions.
That's it from my side.
Okay, sure.
By the way, like, was everyone able to install the Z3?
I haven't installed it yet.
Yeah, so in terms of installing Z3, I think it should be fairly simple. I'd say that just if you guys are familiar with Python, then just install the Z3 Python API directly. It will come with this Z3 binary. So because we'll be using the Python API for a few things later on, so then you can directly install that via pip or whatever Python package manager you're using. So that will be the easiest way, I think.
Yeah, and it's like it takes a while. It can take half an hour to properly install. So, like, don't.
Yeah, if you're building, it'll take quite a bit of time.
I think it automatically starts building Z3.
Mhm.
So, like, it took half an hour for I think, if I remember correctly.
Right.
So, I guess it can take some time.
Yeah. Yeah. So do install this and like see what's like if you have any questions or anything. If it, yeah, sure. So I mean, you guys have like you can go now. If somebody wants to ask anything, they can stay back and ask. Otherwise, they can leave and I'll end the meeting.
Thank you.
Thanks.
Yeah, thank you, man.
Yeah.